Hello, everyone. Welcome to the podium presentation on the topic of bioengineering. My name is Nadia Mohsen, and I'm joined here today by Jennifer Wang. We will be facilitating this session for today. Our first presentation will be by Parin Joshi.
So, hello everyone. I'm Parin Joshi, an incoming second-year mechanical engineering student at U of T. This summer, I've been working with the Cellular Biomechanics Lab, which is affiliated with the Institute of Biomedical Engineering and the Department of MIE. One of the research projects that I had worked on this summer was developing a user interface for an oscillating microfluidic pump. Okay. So user interface design is basically the process which is used for building interfaces in software or computerized devices. Designers aim to create interfaces that users find easy to use and that are introduced to the device. User interfaces can be categorized into three forms: graphical user interface, voice-controlled interface, and gesture-based interfaces. The one that I have worked on is a graphical user interface where the user interacts with the device on a digital control panel. For example, a computer's desktop is a GUI. Previously, a microfluidic pump was built in the lab for generating an oscillating fluid flow, which can be utilized in modeling osteocyte mechanoregulation of breast cancer extravasation. So basically, it was used in vitro experiments for simulating the flow of breast cancer cells into the blood vessels. The Arduino microcontroller acted as the core of the system, and it connected all the components of the pump. The existing user interface for the pump only allows input selection using a laptop, which has made it difficult to use the pump as a separate standalone device. And it also provides just two fluid flow rates. And it also doesn't support customizable input flow rate and frequency values. So the present study investigates devices which would be suitable for developing a compact, easy-to-use user interface and encode an Arduino IDE that would integrate the device with the system of the pump, eliminating the use of a laptop. This will help assist people who don't have a background in programming to use the pump. At the same time, the user interface would be able to allow multiple user input rather than having to choose between just two input values. So looking at the current progress of the design, a pairwise comparison was made to prioritize the objectives when evaluating the design. The pairwise comparison process compares objectives in pairs to judge which of the objectives are more important. A higher score implies a greater importance to the design. After performing this, the size of the design was considered to be the most important metric, followed by the cost and then the practicality of the design. The practicality of the design was tested by its ability to allow anyone without a knowledge of Arduino to be able to use the microfluidic pump for generating the oscillating fluid flow. Following this, Pew chart was adopted to compare the various existing devices based on the prioritized list of objectives, and a confidence score of +1, 0, and -1 was given to the devices against the objective. Finally, all the scores were multiplied with the objective weightage, and the total score was calculated. The device with the maximum score was suggested as the proposed design. So the designs that I had looked at were the TFT Touch LCD, the TFT LCD and the 4x4-inch keypad, and the OLED display with the 4x4-inch keypad. And according to the Pew chart, the 2.8-inch TFT Touch LCD was suggested as it had the highest score among the three. This device could be directly attached to the Arduino Uno board and does not require any other circuit elements for setup. As this is a touchscreen device, it does not require an external keypad, unlike the other display devices. So this fact that it did not require an external keypad suggested that supported the compact design idea. A digital keypad can be integrated within the touchscreen device by writing an Arduino IDE code. And the user can then input any frequency and shear stress value by just tapping on the screen for generating the fluid flow. Now let's take a look at the algorithm, which was used for integrating the TFT LCD, touchscreen LCD with the microfluidic pump and also generating the digital keypad. The first step was importing the touchscreen library from the online Arduino platform and then assigning all the Arduino pins to the corresponding TFT touch LCD pins. Following this, the minimum and maximum touch pressure applied to the screen were allotted, and all the variables that were used for developing the home screen and keypad for the device were developed. After the home screen was generated, the device would then have to ask the user for shear stress and frequency values, which would then take the user to the keypad. The user would be then allowed to input numerical values using the keypad or the numpad, and the input values would then be stored inside the microcontroller. Now, taking a look at the result, the Arduino IDE code for the user interface was tested on Tinkercad by Autodesk, which is an online Arduino simulator, and the code successfully demonstrated the desired output as it is illustrated over here. The figure shows the three important subscreens that will be generated to allow user input for fluid flow rates. So the home screen, when you click on the start over here and the home screen, it would take you to the input screen, which would ask you to input frequency and shear stress values, which would then take you to the keypad where you have the opportunity to enter numerical values, click on the green button, and then the values would be stored in the microcontroller respectively for frequency and shear stress values. Taking a look at the summary, as the existing user interface for the microfluidic pump for generating oscillating fluid flow allowed only 2 input fluid flow rates, and it also depended on the use of a laptop for its working. The present study was adopted to investigate economical devices which are suitable for developing a compact and easy to use interface and also allow customizable inputs by the user. After thorough investigation, various display devices were compared using a pew chart, and the most compact, cost-efficient, and that allowed multiple inputs, the 2.8-inch TFT Touch LCD was suggested. The device could be directly attached to the microcontroller and didn't require an external keypad for input, so this suggested the compact design idea. The code for the interface was developed and tested on Tinkercad and Arduino simulator. The desired output was obtained, which allowed multiple user input, and the pump could function independently. This design will assist people without any background in programming to use the microfluidic pump and avoid any contact between the user and the Arduino code, thereby minimizing the probability of any careless mistakes. The future steps for this project involve testing the Arduino code in person with the setup integrated with the actual microfluidic pump and check if it produces the desired fluid flow. This will be possible once undergraduate students are allowed inside the labs and when it's safe to do so. Here is the list of all the references that were used in this presentation. Finally, I would like to thank the members of the Cellular Biomechanics Lab for giving me this opportunity to undertake the summer research project despite the current unprecedented times. I thank Dr. Lee Dan-Yu for giving me this opportunity to work in her lab. I also extend my gratitude to Henry and Delphine, the PhD students who assigned this project and assisting me with any technical difficulties. I would like to thank UNERD for giving me this opportunity to present at the conference. It has truly been a wonderful experience. Additionally, other than this project, after this was over, in June, I started working on another bioinformatics project, which studied the effects of YAPTAs on, which studied the effects of mechanical loading on osteocytes in YAPTAs proteins. Thank you.
Thank you, Parin, for your presentation. Now I would like to address the judges and ask if you have any questions. Can you please unmute yourselves and ask if there are any? Warren Chen, please go ahead.
Hi, Parin. Nice presentation. My main question is, what are some of the challenges of the coding that you develop? Does everything work, or are there still some challenges that you can, that you might be able to improve in terms of the interface of the system?
All right. So currently, the online simulator Tinkercad was not able to do it completely. So my main aim is to actually use this code in person with the after attaching it with the microfluidic pump and checking if it actually works or not. Currently, for using this Arduino code, I would need the touch LCD, and I do not have access to that right now. So once I get access to that, I would be able to test it physically at my home itself.
Okay, great. Thank you.
Maybe I'll go next. Maybe I'll just follow on Warren's question. So again, nice presentation, and I like these ideas of sort of remove the laptop and just hook up the controller using the device. Maybe a little bit to follow on Warren's question. And knowing that you didn't have the device itself, you came up with the Pew chart, and this is kind of hard to do my video. That it's a 2.8. You said it's a 2.8 inch TFT, right?
Yeah.
Is that how big it is? So you could draw what 2.8 inch looks like. What about the human interface component of it? Like you're using it, like you can program the size of the icons and all that kind of stuff that you're touching, right? How does that factor into your design?
So in the algorithm process itself, the code that I've written is based on the size of the touchscreen LCD. So as I mentioned in the algorithm, first I calculated the coordinates of the system, and then developed the keypad using those coordinates which I found out. So
yeah, I get that. Yeah, that's what I was heading towards. Is sort of we've used these things before as well. And the challenge is that physically they're quite small and they look great, but when you start to actually use them, it's actually quite hard. It's kind of like, using a small phone with fat fingers doesn't work well, and you end up with larger displays. So I just wondering how do you optimize on that, the shape and the size of the icons that you're trying to touch? Do you think that's going to be a problem?
So I don't think it would be that big of an issue, because instead of using your fingers to input the values, there could be a stylus or a pen which would do the work. And I've seen a couple of devices where they actually provide a stylus with the LCD itself, so it might not be that big of an issue.
Okay.
And also, I have made sure that the icons are big enough to be accommodated by the stylus itself.
Great, thanks. Do we have time for one more question? Or not? That's fine, if not.
Sorry, we're running out of time.
No worries.
Thank you so much, judges, and thank you again, Parin, for your presentation.
Thank you so much.